I want you to look at this situation. I hope you can see the situation. The situation is almost set up on my desk right now. I have the detector at the top of the ramp. I'm going to place that car at the top of the ramp too, where I will release the car while taking data. A graph shall ensue. One for position, one for velocity. What will they look like? Sketch them, please. Now, I'm saying this, and I'm not trying to be mean, but if you are just trying to do it from memory, you're doing it wrong. Because you could guess wrong, and then you'll be part of that percentage that I don't like so much. So check things. Think of things. Also, I need to tell you that from now on, because I've made an accommodation for one student, I will try to post. It's not outlines and it's not my notes, but it's kind of the things you should probably know by the end of a class period. I'll be posting them each day. The person wanted me to post notes and stuff as part of their accommodation. I really just don't have anything like that to give you, but I'll create this document and I'll put it in the calendar every day so you all have access to it. So whatever I accommodate for one, I try to accommodate for all. So, I'm just going to let you have a few seconds, and then I want to come and check your work. So I'll actually do some of the shutting up now, and I'll give you some moments. I have had an opportunity to walk around the room. Although not filled with disappointment, I am harboring some disappointment. So, I'm going to say some things, and let's see if by the things I'm saying, you are, I'll use the word triggered into perhaps making some changes. Remember, what I want you to observe is the car starting at the top of the ramp and being released. So, let's look at, say, your position graph. At time 0, is the object close to the detector or far away? You don't have to say a word. I just want to see people look at their picture. At time 0, what is the object's velocity? Is it moving at time 0 or is it stationary? Since the slope of the position graph is the velocity, is the slope of the position graph matching where the dot is on the velocity graph? Meaning, whatever the velocity is there a corresponding slope on the position graph? As time goes on, is the object moving in a more positive direction or a more negative direction? Remember, the motion sensors see all positions as positive. Is the object's velocity becoming a bigger number? And if so, is it bigger in the positive direction or bigger in the negative direction? Remember, away from detector, positive velocity. Towards detector, negative velocity. And is the object its slope for the position graph? Does it match up with the velocity? Meaning, at time 0, the object's velocity is probably 0. It's released from rest. At time 0, the object's position is probably not 0. But it's probably close to 0. I'm saying it's probably not 0 because we know the detector can't see anything until 20 centimeters. So although you might have put that dot at 0, you probably should have put it like right there. But I would forgive you if you put it at 0. No big, no skin. On the other hand, the slope of the position graph should mimic the velocity. The slope of position is velocity. The velocity is 0, so the slope of the position should be 0. The slope of the velocity graph is acceleration. I've not done this one before, but at the same time, there's no reason we shouldn't. It's going to accelerate away from the detector. That's a positive acceleration. I'm expecting the velocity to be positive. In fact, after some period of time, I suspect the object will be over here someplace with a positive velocity, indicating it's increasing its position away from the detector. I would suspect that a straight line could be used to connect those two. I suspect that because the slope of the incline stays the same all the time. So I expect the acceleration to remain the same all the time. I think the slope of the dot at the end will be the same as the slope of the dot at the beginning. At the same time, after a period, the position will have become more positive. The velocity of this point, whatever that number is, has got to be the slope over here. Which means graph that should look something like this. Now, I'm not getting 100% compliance here, but I need it. Thus, yesterday's activity was to help reinforce this. But you should be aware. On your test, we took, 7-8 minutes to do this? On your test, this is a multiple choice question where there will be 5 pictures of unlabeled graphs. Concave up, concave down, straight lines, curved lines, all of it. You'll read the scenario, you have to pick one. And you'll have to maybe go through this idea in your head so that you can decide which one of these fits the case. And you're going to have to do it quickly. I'm not sure memorization is the right way to go, though. Yes, sir?
Do you know if there will be such a small change as the object starting at the origin and not a little bit further away from it?
I think that was me just throwing it in there to rub it in your face a little bit. But I don't want to cast it out of hand. There should be a reasonable expectation. But also, for what we're about to do next, I kind of need to put that out there. Because what we're about to do next is partly in line with what the lab is about. I want to remind you that this is not a surprise. We know from looking at the motion equations that there is a mathematical model that we are expecting for each of these. For constant acceleration, we are expecting a linear model for the velocity. And for position, we are expecting a quadratic model for the velocity, for the position. Those are the mathematical models, the basis for them at least. The only difference is that instead of putting delta x, I've changed it to x minus x naught and moved the x naught to the other side. That way, these are functional relationships. X as a function of t. And along the bottom, that gives me 3 initial conditions. Where is the object at time 0? How fast is it going at time 0? And what was the acceleration at time 0? That's why when you put in 0 for t, you're left with x naught, x at time 0. Similarly, I've got the same 2 initial conditions related to the velocity. I don't have position, but also it's a functional relationship. At time 0, put in 0 for t, I'm left with v naught. That's right, that's the velocity at time 0. So what I'm expecting you to do for your lab is to conduct the experiment, meaning set the car up in such a way that you can actually acquire the right kind of data. I have set up such a lab, but it's a 5-second lab, and I'm pretty sure it doesn't take 5 seconds to go from there to there. So I think 3 seconds. And 50 samples per second. And let's see if we can't acquire a set of data. You can't what? What are you hoping to see? I mean, I think it'll work.
See if you log out for a second. Say that, dude. He's confused. You just said I can't see it, and you don't see it.
It's okay.
Are you handling him?
Yes.
Get him under control, will you?
I'm trying.
All right, or kick him off the island. One of the two. Something has to happen here. All right, do you really have a question? No, I'll be happy to answer it. Happy's not the right word to use, but I will answer it. All right, so I'm gonna try and coordinate with my lab partner, apparently my right hand, and here we go. Ready, set, go. I don't like my data. I'm gonna try it again. Because that only took 3 seconds. I don't think I have a problem with this. Ready, set, go. It's very similar. I think it's because I'm starting too close to the detector, so I'm going to come a little bit outside that range, so I'm not inside the detector's range. Ready, set, go. So I think that took about 8 seconds total, maybe 12. So for people who are worried why it's taking so long, I couldn't tell you. I will say that I got this at the end. I'm not particularly happy about that, but I don't know what else to do. And clearly, I get the same little wiggles every time I've done it, so there's something with the track. I don't know what it is. But either way, I believe I'm seeing a model for the behavior of the car. Now, in order to analyze that, I clearly have a curved portion that's there for the position graph and what looks like a moderately straight line version for the velocity graph. I'm going to choose a generous amount of the data as much as possible. It doesn't include the part at the end where I hit it with my hand and stopped it. I'm going to plot a curve fit, make it linear. And these are some details I think you should know, because you might not be able to read them from where you are. But it seems to me the value of m is 0.3144, and the value of b is 0.07393. Mathematical model. V is a function of t. I'm going to write these down. I know you can't see it, but here, I'll let you see it. 0.3144t. That's the value for m. Plus, what was that value for b? 0.07393. So I'm just reading it off of the linear regression, but that is my mathematical model for the velocity versus time graph. So in order to get the mathematical model for the position versus time graph, I'm going to select the portion of the graph that seems appropriate. Choose apply curve fit, but it's not linear. I want to choose the quadratic. Now I'm looking to see that the two red lines kind of overlap each other. When I had linear, I mean, clearly the linear graph doesn't seem to line up with the curved nature of the quadratic. So you choose a curve fit that best seems to fit the data set. All right, so I have the value for A is 0.1559. The value for B, 0.0802. And the value for C, 0.21. Now, x as a function of t equals 1/2 a t squared. I want to use the functional relationship we have. The value for a isn't exactly what I want over there. I want to preserve the relationship we developed in class. So I'll have to take whatever I got for a and double it. It was 0.1559. So when I double that, I'm going to get let's see, that's going to be 1,
1, 2.
I was going to say 2, but okay, 0.3118. Plus the value for B, 0.802. 0.0802. T plus 0.21. Now, it might not be obvious to you, but there's some things here that are very important to me that I hope you will notice. The accelerations are very similar. I expect that. It's based on the same data. In the same way that the initial velocities are very similar. I expect that based on the same data. But it also did tell me that it started 20 centimeters away from the detector, because that's the initial position at time 0. It gave me 0.21, that's 20 centimeters. But there's something more here that I want you to understand. And this is where we're going to be leaving the whole lab portion and going into the part of this discussion that has merit, that's really important to me. So first, do you see what I'm expecting you to do for your lab? Pretty straightforward. Any questions about this? Yes.
Just for a quick recap, so we write down our motion equations like those two for each graph, and then we write down our combined accelerations that we found across all of them at the very end of the 7th page.
You tell me if the accelerations that you found for all of them look to be the same.
That's it. Okay.
Don't take that for granted. I've done this lab, and more importantly, even 3rd period, we did the up and down version. You get a different acceleration when it goes up and down than you do here. There's a reason for that. So yours might work out to be the same, but in most conditions, you'll probably see a difference if you have your cart make both parts of the trip. The reason is friction. Friction acts to change this number when you go up and back. And it's different when you just go up or you just go back. So be careful, look at your data closely. So here's what I want you to understand, and this is the part where we're going to be transitioning. And those of you who are in calculus, this has a familiar ring to it. You guys who are not in calculus, this is going to be unfamiliar. You need to pay very close attention. I don't know how to say that any more than not your normal, I'm just going to write down what Mr. Shelton is putting on the board. You need to write some things down. The reason I bring it up is because I'm desperate for you guys to see that there is a connection between the velocity that you have on your velocity graph and the slope of the position graph. And even still, even today, when I walked around to see your work, I still have people who are having difficulties making that connection. But I need you to come to grips with the fact that this number right here represents the slope right here, how steep the curve is. Because one thing I'm going to want you to eventually do, and what our math should do for us, is be able to tell me what the velocity is right there. I don't have that on the position graph directly. There's a way for me to do this on the position graph. And I know you're familiar with probably what I would have to do on the position graph to figure this out. I would probably have to grab a straight line. Try and make it look tangent. And then find the slope of that tangent line. Because that would give me the slope at this one point on the graph. Then if I decided I wanted the velocity here, the velocity there, you'd have to come up with a different tangent line. Find a different slope. But you have an equation that tells you all the slopes. If I tell you that this moment in time was 1.7 seconds, yeah, you could do the process of putting in a tangent line, or you could plug in 1.7 seconds here, and it will tell me what the slope is on the position graph, because I have an expression for the velocity. Newton saw this arrangement. He saw that what he was getting from the algebra, remember, we got all this from algebra, right? We found the slope of this line using rise over run and turned that into a formula. We then found the area of that curve, and from the area developed a combined relationship that gave us the position as a function of time. We developed all of it from algebra. Newton saw that and realized there might be a way to engineer a new equation, a new function, once you had one of the functions. What I mean by that is he believed that if I gave you any of these functions from either experimental data or from some kind of derived formula, that once you had one of these, that there was a way to figure out what all of those functions were. Because he knew that this one is the slope of this is acceleration. And the slope of this is velocity. So he tried to find a process, a method for figuring out how you could develop one function based on another. He's not working in the dark here. There are other mathematicians who are also working on this idea. And they understand, because there is already a strong foundation in algebra, that finding the slope is related to finding how things are changing. Right? We define slope as the change in the horizontal and the change in the vertical. Right? The vertical divided by the horizontal. So velocity is delta x over delta t. Acceleration is delta v over delta t. The big problem is that I can't just pick 2 points here and figure out the slope. I could pick 2 points on my tangent line, but if I try to pick 2 points on this line, I'm just getting an estimate for the slope, because this line is curved. The tangent gives me the exact slope, but I'm estimating here. Mostly because the delta t is super small. That's the real problem. The delta t part starts getting smaller and smaller and smaller as those two green points get closer and closer together. So now here's where I'm going to stop. The people who are in calculus, they're learning this thing called, who's had it already? Who's done with the calculus class? See, these Yagos think they're way smart. And they think that because they know things. They know things now. They know all the stuff I'm saying. And they know that what I'm going to teach you is like super easy. But it wasn't easy when they first learned it. They had to learn the fundamental theorem of calculus, which is the thing that all the people who are in A, B, and BC right now are just starting to get to. And they're finding that thing to be not particularly fun to deal with. You guys who are in A, B, and BC, have you guys brought that up yet?
BC's done.
Oh, you'll be coming soon. BC's done, so AB hasn't gotten there yet? Yeah. You guys in BC who just covered it, fun times? That's usually not anybody's recollection. I want you to think of this for a moment. This is something that I am sure all of you know intimately well. You all are very aware that if I take the natural log of b and minus the natural log of a, I could get the same answer by doing the natural log of b divided by a. I'm sure you know this. It was in Algebra 2, which I'm sure you have a stranglehold on. Here's the thing. Even if you do remember this, and just so you know, most students, they forget this, in the same way they forget what the surface area of a sphere is. Raise your hand if you can tell me that formula. Aww. Really? Sorry.
It has a point.
You were taught it, but how about the area of a regular octagon in terms of its side length?
Just make it in a triangle.
I mean, what I'm saying to you guys is you learn these things. Had to prove them probably, just like you had to prove the alternate interior angle theorem. That doesn't mean you can state them now, let alone prove them. I don't think there's a person in the room who can prove this to me, even if you did remember it. I'm saying that not to be mean. I'm saying that people in calculus know how to do what I'm going to teach them. They don't necessarily know why. And they're going to know what I'm going to teach you. They don't necessarily know why. They can't go back, in most cases, and prove using the fundamental theorem of calculus how to take what we're going to call the derivative. The only person that took me up on this challenge was expected to and is gloating already on Remind. So you guys see Juan, make sure you tell him how proud I am of him and how excited I am that he's going to talk to me about it all day tomorrow, how he used the fundamental theorem of calculus to prove that the derivative of ln of x is equal to 1 over x. When the truth is, I really don't care. Not even a little bit. Not because I don't find it exciting that he went out and did it, but because math is a tool. You take a math class to prove why it's true. We want to use it here. And that's the thing. I want to use the tool as it's intended. You have been taught algebra. And algebra, by definition, allows us to look at the relationship between numbers. That's what it means. Algebra is the relationship between numbers. We develop a relationship, and we state that this relationship is true for all the numbers for which we could put in for our value. For example, I have a relationship right here. It's a pairing of numbers, right? For every possible value of t, there is a value of v. I tell you a time, you'll give me a velocity. Algebra is that relationship. I don't have to know every possible time ahead of time. I have a relationship that holds all of those things together. So if I want to know how fast the car was going at 1.4 seconds, you could tell me. And how fast the car was going at 50,000 seconds, you could also tell me. It has paired together every number in the existence of numbers. That's what algebra does. It finds the relationship between numbers. What I'm here to tell you is that there is a relationship between this function. It is all of the slopes that exist for this function. For every single time where I can tell you where the object is, this formula will tell you how fast it's traveling. Calculus tells me how to find these relationships, the relationship between functions. That's why calculus is known as the algebra of functions. Algebra is how numbers are related. Calculus is how functions are related. So what we're going to do is learn a process by which if I give you one of these three things, you should be able to give me the other two. That's what we're going to learn how to do using calculus. We're going to learn it for only a very small, narrow number of cases. So we're going to use what's called the Polynomial Rule, sometimes referred to as the power rule. We'll eventually learn the sine and cosine rules. And lastly, we'll learn the exponential rule. Now, there are lots of rules for calculus. And for those of you who are in calculus or have had calculus, it is possible to use more in this class and perhaps develop an even deeper understanding. Things like the chain rule and a few others will serve you okay. It's unnecessary. In this class, we treat this not very different from just looking up the formula for the surface area of a sphere. All of these rules are on the equation sheet. It's not expected that you be an expert in calculus, just that you know how to use the rules. Okay? Now, to understand the rules, you are going to have to understand that there is some symbology involved. And I will need you to use the symbology involved. Velocity is defined as the slope of the position graph. But this symbol the delta x and the delta t, is only good in conditions where the velocity is a constant. To deal with a situation where our velocity is changing, we have to use a different symbology here. A symbol that means that the velocity is different at all the different points. It's not a huge difference, but it's the symbol we use to indicate we're taking a derivative. We move from using delta to moving a lowercase d. They are functionally different. One of them tells you to take 2 points and find the difference in the y and the difference in the x. The other one is telling you to take the derivative of your position function. So notice the way I'm rewriting it a little bit. I want you to note that this is saying to take the derivative of your position function. It actually says more than that, and I want to be clear about what it's actually saying. It's saying take the derivative of the position function with respect to the variable representing time. That's what this says. Take the derivative of the position function with respect to the variable representing time. This is a new word for you, and it's okay if you don't fully appreciate its meaning, but that's what this is saying to you. I'll say it for a third time, so I think it's appropriate to translate this. Take the derivative of the position function with respect to the variable representing time. Now, familiar? This would be me saying to you, take the derivative of the function for y with respect to the variable x. That's what it's saying. Now, to translate that, it means that treat every variable that's not x as if it were constant. It's just a number. And treat the variable in the denominator as the most important variable in your polynomial. It's the one that the rule applies to. The rules apply to the function variable. So I'm going to teach you a rule, but that rule applies to the function variable. Now, we're not going to get the rule today because the bell rings in 1 minute. So tomorrow is very much, to me, a critical day. There will be no surprises tomorrow, as you already know the answers to every question I'm going to ask you tomorrow. They're on the board behind me, I promise. But you're going to see how they work tomorrow.